Hello, my name's Alistair Forsyth, and welcome back to Discrete Calculus with the Wolfram Language. This lesson will go over the harmonic numbers. Getting started, the harmonic numbers are defined such that the nth harmonic number, h sub n, is equal to the sum of the reciprocals of the integers from 1 to n. The harmonic series is defined as the sum of the reciprocals of the integers from 1 to infinity, or the limit as n grows without bounds of h sub n. The generalized harmonic numbers are defined such that the nth generalized harmonic number of order m is the sum of the reciprocals of the integers raised to the power of m from 1 to n, and this is often denoted h sub n comma m. Moving on to some properties of the harmonic numbers, most notably they have a recurrence relation, namely h sub n is equal to h sub n minus 1 plus 1 over n for any n that's an integer with n greater than or equal to 2. Along with that, Euler's constant gamma is defined using the harmonic series. According to Knuth's book, Concrete Mathematics, the definition can go the limit as n grows without bounds of h sub n minus the natural log of n is equal to gamma. We can show this within the Wolfram language using its asymptotic function, taking asymptotic of the harmonic number n minus log of n as n grows without bounds. And if we evaluate this, it comes out to be Euler's gamma, as we thought. Moving on, the Riemann Zeta value of m can be described as the limit as n grows without bounds of h sub n comma m as long as m is an integer greater than 1. Now this works because the Riemann Zeta function is classically defined as zeta of m is equal to the sum of the reciprocals of the integers raised to the mth power from 1 to infinity, which is very similar to the definition of the generalized harmonic numbers. And we can also use the Wolfram language to show this. If we use the equals equals operator to ask the Wolfram language whether zeta of m is equal to the limit of the harmonic number of n comma m as n grows without bounds, it returns true if m is greater than 1, which is what we expected. Now you can probably tell from these pieces of code, but the harmonic number of n in the Wolfram language returns the nth harmonic number, and harmonic number of n comma m returns the nth generalized harmonic number of order m. Moving on, the harmonic series is actually divergent, which is somewhat unintuitive to some people. There are many proofs of this, but my favorite comes from Leo Goldmacher of the University of Toronto, and is as follows. Suppose the harmonic series does converge to some value h. In that case, h would be equal to 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6, and so on and so forth. This implies that h is greater than or equal to 1 plus 1/2 plus 1/4 plus 1/4 plus 1/6 plus 1/6, and so on and so forth. If you missed what we did here, we simply changed 1/3 to 1/4, 1/5 to 1/6, 1/7 to 1/8, and so on and so forth in a similar manner. Now grouping these like fractions together, we can see that h is then greater than or equal to 1 plus 1/2 plus 1/2 plus 1/3 plus 1/4, and so on and so forth. However, this then implies that h is greater than or equal to h plus 1/2, as when we grouped those like fractions, we gained a 1/2. This then generates a contradiction because h cannot be greater than or equal to h plus some value, meaning that the series cannot converge. Moving on to some notable applications of this. Suppose you stacked a deck of cards on the edge of a table such that each new card is added starting at the center of gravity of the stack. For example, you would place the first card just on the table, the second card with its back at 1/2 through the first card, then the third card with its back 1/4 into the second card, and so on and so forth. As Knuth points out in the book Concrete Mathematics, you can actually model this situation using the harmonic numbers. Here, I've included a visual from the Wolfram Demonstrations project, which will show how this card stack will grow without bounds. If we start with one card, it'll only be 1/2 over the table. Then as we increase, it gets farther and farther and farther, till we eventually hit however many cards are here, and it is over 2 full card lengths away from the table. This demonstrates that the nth card added actually adds 1 over n of the card's length to the total length of the stack, making the total stack length h sub n minus 1. Now what's unintuitive about this is that because the harmonic series is divergent, this implies that you could make a stack of any length with enough cards. If you're curious about this, I'd implore you to grab a deck of cards and start trying it. However, it is very hard to reach a place where you're even one card away from the table, let alone infinite cards away from the table. Another application of the harmonic numbers could be menial record breaking. Suppose you aspire to create the world's tallest marble stack. We're going to assume here that there is so much luck involved with stacking marbles that any skill gained along the way is completely negligible, meaning no trial has any influence on any other trial. Because of this, since each trial has an equal chance of being the tallest, the chance of setting a new personal record is actually proportional to the number of trials. For example, if you tried 10 times already, there's a 1 in 11 chance that your next attempt will be a new record. To understand the reasoning behind this, imagine you're blindfolded for the trials and someone else records the height. Without knowing the height of any given trial, each trial has an equal chance of being the highest. So if you have 11 trials that you all look at the same time, each given trial has a 1 in 11 chance that it's the tallest. Now we can apply this logic for already having done 10 trials and adding another one, giving you a 1 in 11 chance that your next attempt will be a new record. Taking this one step further, we can examine each individual trial, noticing that the first trial has a 100% chance of being a new record, the second has a 1/2, the third a 1/3, and so on and so forth until 1 over 11. So over those 11 attempts, you can expect to set a new record roughly h sub 11 times. Using the Wolfram language, we can see that if you aspire to create the world's tallest marble stack and you try it 11 times, you can expect to set a new record around 3.02 times. Now, using all of these bits of harmonic number knowledge, I have a little puzzle for you to solve. Suppose you have a single lane, one-way road with no passing allowed. How many separate clusters of cars can you expect to form for any given number of cars? I originally found this question from a YouTuber, Zach Starr, who has an excellent YouTube video going over the property. Along with that, I have a little hint for you. A car will only form a new cluster if it is slower than the one in front of it. You can pause here if you don't want the solution revealed. However, before we make a formal solution, we're going to model this situation using the Wolfram language. Here, I have a chunk of code that first takes the number of cars you want to run and the number of trials you want to run. Then it creates an empty results vector, which we'll populate later. Then we loop through by the number of trials we have, get the number of cars. Then we create a vector of random integers from 40 to 70 with the size of our number of cars. That way, we can model each driver independently picking a speed from 40 miles an hour to 70 miles an hour. Then, we assume that the slowest car is the first one, and we set our number of bunches to 1. We do this just because the first car we know will be slower than the one in front of it because the one in front of it isn't there, and also there can be a minimum of 1 bunch. Then, we loop again through every value in the cars vector, and if any given element is less than the slowest car currently, then we set the slowest equal to that element, and we add 1 to the number of bunches. Then, after that inner loop, we append the number of bunches to the results vector. Then, this little piece of code just takes the sum of each part of the result vector and divides it by the length of the result vector, giving us the average number of bunches. So all in all, what this chunk of code is just doing is repeatedly running trials of this situation where each car randomly has a speed from 40 to 70, and see how many bunches form. Now, let's run this a couple times with 4 cars and 1,000 trials. First, we get 2.069, then we get 2.025, then 2.048, and then 2.08. Now, you might have noticed a pattern here, but if you didn't, all of these outputs were very close to the harmonic number of 4. We can repeat this simulation again with, let's say, 20 cars. First, we get 3.353. Then we get 3.331. Then 3.318. And then 3.366. We can check our results again, and this time the harmonic number of 20 comes out to be 3.59774, which all of our outcomes were very close to. Now there is some margin of error in our simulation because it's not instantly going to converge to the harmonic number of 20 because we only have around 4,000 trials. However, it's impressive to me how close it comes out. Now, onto a formal solution. For any car to start a cluster, it must be slower than the one in front of it. However, if it is slower than the one in front of it, this also implies that it must be the slowest car at all so far. So, given that each car has a random driving speed, each car actually has an equally likely chance of being the slowest car yet. Therefore, just like with marble stacking, with n total cars, you should expect the total number of clusters to be around h sub n. And now you've hit the end of this video. Thank you for watching. In this lesson, we went over harmonic numbers, the harmonic series, and the generalized harmonic numbers. We went over some relationships between the harmonic numbers and the Riemann zeta function and Euler's gamma constant. And we went over some different problems that can be solved using harmonic numbers. In the next lesson, we'll go over some more tools for manipulating sequences and series, namely permutations and combinations. Again, I'm Alistair Forsyth, and thank you for watching. Bye-bye.